Leah here from LeahFirstSci.com. In this video, I will take you through another common type of NMR problem where you are given a set of molecules, one or more graphs, and asked to match them up. In this case, we have 5 molecules and 1 graph, but instead of trying to look at the molecules and compare it to the graph, I'm going to show you a different trick, and that trick is to guess what the graph will look like for each of the molecules and then match it to the graph given. This trick is especially useful when you are given multiple molecules and multiple graphs. For each of the molecules given, we'll try to determine the number of hydrogen types, the splitting that we expect to see on each peak, the number of neighboring hydrogens for each peak, and finally, the chemical shift along the graph. If you are not comfortable with these topics, go back to my previous NMR video to see why and how we utilize these tricks. If you are ready, then let's go. For molecule A, we are given a substituted ketone. Let's use different colors to identify the different types of hydrogens. On the right, we have 3 terminal hydrogens. The second carbon has a ketone and therefore has no hydrogens. Moving leftward, we have 1 hydrogen on a tertiary carbon, and then we have 2 sets of 3 equivalent hydrogens on the terminal carbons. The terminal carbon is attached to a carbonyl, which means it has no hydrogen. Therefore, the purple hydrogens have no neighbors, will have no splitting, and will give me 1 singlet worth 3 hydrogens. Moving over to the red hydrogen, on one side we have a carbonyl with no hydrogen neighbors. On the other side, we have 2 methyl groups for a total of 6 hydrogen neighbors. Using the rule n plus 1, we get 6 neighbors plus 1 for a septet, also referred to as a multiplet, which will probably look like a mess on your graph. Finally, on the left, we have 2 sets of 3 equivalent hydrogens, which means they will show up as 1 peak, and they only have the 1 hydrogen neighbor to the right. N plus 1 gives me 2, which means I'm going to have a doublet. Last but not least, we want to guesstimate the approximate shift for each peak. Since the singlet is by itself, it is located next to a carbonyl carbon which is partially positive. It will be somewhere in the boring region. We can guesstimate a shift between 0 and 2. The septet, being located near the carbonyl, and all these terminal hydrogens, it will still be located within the boring region, meaning somewhere closer to the right. However, this will likely be the most exciting group on the molecule, given how many different groups are next to it. So we'll write high between 0 and 3. And finally, for the doublet, given that it's at the end of the molecule, but it's next to another carbon with a hydrogen neighbor, we'll also keep it on the boring region and say the shift is approximately 0 to 2. We'll estimate the numbers from 0 to 12 without worrying about the particulars. Instead, what we want to look at is the relationship between the groups in terms of which peak is more to the right and which peak is more to the left. Since the green doublet is the group that's farthest away from the carbonyl, this is going to be the most boring group and therefore the most to the right. So we'll start out with the green doublet somewhere near 0. The methyl group all the way to the right is located near a carbonyl but doesn't have anything else exciting next to it, and so we'll assume that is the second group and draw a singlet somewhere left of the doublet. And last but not least, our single hydrogen that has the multiplet or septet is the most exciting, being surrounded by all these groups, and so we'll draw that as the leftmost group with a quick scribble to represent all the 7 peaks. And this is what the graph would look like. I unwittingly gave you this as choice A, so let's take a quick look back at the graph given, and lo and behold, it looks pretty much like what we predicted. This is our molecule as we drew it out. We put our doublet all the way to the right, and notice that it represents 6 hydrogens, which is why we have the number 6 over the integration value. We gave that single red hydrogen a multiplet all the way to the left, and you can recognize that we have 1 hydrogen represented by this scribble. Many times when you see a multiplet on the graph and are unable to tell exactly how many peaks, you will be given an expansion that tells you where it came out of the graph. So notice that we have 2.6 to 2.7, which is approximately between 2 and 3, closer to 3. But in the expansion, we can actually count the tips here. 1, 2, 3, 4, 5, 6, 7. And yes, this is the septet that we predicted. And last but not least, our methyl group that has no hydrogen neighbors is represented by that middle singlet at approximately 2. Now let's assume that you're not sure this is the correct answer. Let's continue the process of predicting what each graph would look like so that you are confident with the choice we picked and also know how to recognize other graphs in case they come up in your quizzes or exams. Are you struggling with organic chemistry? Are you looking for information to guide you through the course and help you succeed? If so, download my ebook, 10 Secrets to Acing Organic Chemistry, using the link below, or visit leaforsci.com/orgosecrets. That's ORGO secrets. If you enjoyed this video, please give it a thumbs up and even share it with a friend or two. If you have any questions regarding this video, leave a comment below or contact me through my Facebook page at facebook.com/leaforsci. There will be many related videos posted over the course of the semester, so go ahead and click the subscribe button to ensure that you don't miss out.